So we have seen DO, that is the dissolved oxygen. So normally what happens is that every the gas has a tendency to get dissolved into the liquid. Here our gas considered is oxygen and the liquid considered is water. So how the gas or how the oxygen will get dissolved into the water? Because oxygen is putting some partial pressure. So the according to the Henry's law, greater is the partial pressure, greater will be the amount of oxygen that will be getting dissolved into the water, right? So the oxygen getting dissolved into the water is just because the oxygen, the atmospheric oxygen, is putting some partial pressure on the surface of the liquid, right? So now the best example of the gas getting dissolved into any liquid is the your Coke bottle, right? So if you go into a canteen and purchase a Coke bottle in the sense Pepsi, Coca-Cola, anything, and when you open it with the help of the opener, when the lid is open, the gas escapes, right? So you hear a noise, and also you get a sense of bubbles coming out. So what is that gas? That gas is nothing but CO2 that is made dissolved into that particular colorful liquid because there was high pressure. Now that you have removed that high pressure and the liquid is brought to the atmospheric pressure, what has happened, that gas has got escaped, and then now it is now that you can drink. Now why that CO2 is dissolved into that liquid? So to keep that liquid fresh, and even that you get a typical smell and a taste because of the CO2, because the CO2 was earlier dissolved into that Coke bottle, right? So gases getting dissolved into the water is also a natural process. So in natural process, in the sense, even when you go into the river water, when we get a river water and do the dissolved oxygen analysis, we get a DO content into it. Why that DO content is there? Because naturally the atmospheric pressure is putting some atmospheric oxygen is putting some pressure on the liquid surface, and because of that the oxygen is getting dissolved. Now with the help of the dissolved oxygen experiment, what we have did is we have calculated what is the oxygen dissolved, how much quantity of oxygen is dissolved into that water or the given sample. How we have found out is a complete set of experimentation what we have did, and depending upon the value we are going to decide whether that liquid or that particular sample is polluted or not polluted, right? So when the DO value for the aquatic flora and fauna to flourish in the water, some quantity of oxygen is required, right? That oxygen quantity is 2 mg per liter. So when the dissolved oxygen in the water falls below 2 mg per liter, what will happen? That the fish and the plants inside the water will start experiencing some difficulty for their growth, and eventually when the DO is reducing, what will happen is that the plants and the aquatic flora and fauna will slowly start diminishing, right? In many of the cases, in the I'm talking about the DO which is less than 2 mg per liter, but in many of the water bodies today, what has happened, the DO is already less than 2 mg per liter, and even it is reaching towards 0 mg per liter. So if I take a sample from a gutter which is used for flowing the sewage, what will happen? I may get the DO value as 0. Why that DO value is 0? Because it has a large quantity of the organic content, and because of that it requires huge there is no possibility of oxygen getting dissolved there. So hence it is the DO is coming out to be 0. So now we have seen that the DO varies with the temperature, it varies with the pressure, or it varies with the height as well, it varies with the salt concentration, and it varies with the it varies with the organic matter. So higher is the organic matter, lesser will be the DO, right? Higher is the temperature, lesser will be the DO. Higher is the height, lesser will be the DO, and higher is the salt concentration, lesser will be DO. So in explanation video, I already told you, if I take a salt water and a normal water, so salt water will have, or a marine, saline water will have less DO because it has a huge salt concentration. So if I take no normal water and a sewage, and if I find out a DO, so DO of sewage will be it will be less. Why? Because it has a high organic matter, so it will be requiring a very it has a very no very less DO, right? So all these are important. Now because of a DO value, so if I get a DO value less than 2 mg per liter, we say that the sample or that particular water is polluted, right? If the if the DO is 0, then we say that the dissolved oxygen is absent and that water is said to be again polluted only. So again, I am trying to make a point here that even if the DO is less than 2, or even if the even if the DO is coming out to be 0, we say that it is polluted. But how polluted, we cannot judge it with the help of the dissolved oxygen value. Or for no, to give a good example next, if I am having two samples taken from two factories, right? And the factories that are giving out that particular wastewater are the wastewater is very polluted. If I find out the DO of the samples collected from two factories, the DO will be 0 only. But if I have to decide if which factory is polluting more, so I will have to find out the pollution strength, right? So DO value will only give you the idea whether the sample is polluted or not. But if I have to find out what is the pollution strength, DO value is not going to help me out. So what I have to do is I'll have to use some different parameters. So different parameters we have already seen an experimentation regarding biochemical oxygen demand. In biochemical oxygen demand, what happens is that it measures the amount of oxygen that is required to that is required for the oxidation process of all the organic matter by the heterotrophic microorganisms. So what I mean to tell here is that there is if I have to what is the BOD? It is the oxygen required to oxidize all the organic matter, right? So here organic matter, that word is very important. It is the oxygen required to oxidize all the organic matter by the heterotrophic microorganisms, right? And no, we find out the BOD value with the help of the DO depletion, right? So now what will happen is that the DO earlier the unit of DO was mg per liter. Here also we have the BOD unit as mg per liter. But now here the understanding of the concepts of DO and BOD are different, right? DO is the oxygen dissolved into the water sample, and what is the BOD? BOD is the amount of oxygen that will be required for the complete oxidation of organic matter only by the heterotrophic microorganisms. Now, the oxygen required to oxidize all the organic matter. So why the oxidization of the organic matter is required? If I oxidize all the oxygen, if I oxidize all the organic matter, what will be happening? My water will be more pure, right? So my water is containing organic matter, hence it is polluted. But if I oxidize all the organic matter into all the organic matter from it, so what will be happening? All the organic matter will get removed, and my water will my sample will be more pure, or it will be having less pollution, right? So oxygen is required for oxidation of all those organic matter. So how much oxygen is required, that I am going to calculate. If the oxygen requirement is more, my wastewater will be more polluted. If my oxygen content is less, my water will be more my water will be less polluted. So if I'm getting a BOD value like 2000 mg per liter for one sample, let's say sample A, and if I'm getting the BOD value for another sample as 100 mg per liter, let's say that is sample B. So amongst these, the sample A is more polluted. Why? Because for the oxidation of all the organic matter, it requires more oxygen, that is 2000 mg per liter. And in sample B, that is sample B has got BOD as 100 mg per liter. That means that it requires less oxygen, or it requires 100 mg per liter of oxygen for the oxidation of all the organic matter into it. So higher is the BOD value, higher is the pollution strength, or we can say higher is the pollution in that sample, or lesser is the BOD value, lesser will be pollution into that sample, right? Now in BOD, we were finding out the oxygen required for the oxidation of organic matter only. Now what is, now we are going a step ahead, and what we are going to do in chemical oxygen demand is that, see, you must be getting on your screen. So now what is the chemical oxygen demand? Chemical oxygen demand is a measure of the total quantity of oxygen required for the oxidation of nearly all organic compounds in wastewater by the oxidation of, by the action of the strong oxidation agent. Here what we are going to do is, here we are going to, we are not only going to restrict ourselves with only the oxidation of organic matter. Here in COD, what we are going to deal with is oxidation of all oxidizable matter. So oxidation of organic as well as inorganic oxidizable matter, that we are going to consider in determination of chemical oxygen demand. So no, when I say BOD, BOD is only the oxygen required for the oxidation of organic matter, while COD is the total oxygen required for oxidation of all oxidizable matter. So let it be an organic compound or inorganic compound. If it is oxidizable, then it is considered in a COD. So I think so. Basically, now that I have a question to ask. So if I'll be repeating my two statements, and then you can tell me. BOD is the oxygen required for the oxidation of organic compounds, and COD is the oxygen required for the oxidation of organic as well as inorganic compounds. So tell me if the COD value will be higher or BOD value will be higher. You can tell the right answer. The COD value will be on the higher side. Why? Because the oxygen required for the oxidation of organic plus inorganic compounds will be naturally high, right? So that is very evident, right? So the answer is right. So now how we are going to do that, also we are going to see. So here I'll be just reading out the statement. So potassium dichromate, that is K2Cr2O7, is the chemical oxidizing agent that we are going to use, as it can oxidize a large variety of organic substances into CO2 and H2O. Aromatic hydrocarbons and pyridine are exceptions; they remain unoxidized, right? So here, in case of COD, we are going to use potassium dichromate, that is K2Cr2O7, which is a very good chemical oxidizing agent. And if if we prepare K2Cr2O7, the normality also do not change. So it is a very good, and it has been applied for the finding out of COD. So here you can see, the chemical oxidizable matter. When I say an oxidizable matter, so it can be an inorganic oxidizable matter as well as the organic oxidizable matter. So in organic oxidizable matter, we are going to deal with the non-biodegradable and the biodegradable as well here. And in inorganic oxidizable matter, we are going to deal with the cyanides, ferrous compounds, nitrates, chlorides, sulfides, everything. So previously, when we were dealing with the BOD, so when we were dealing with the BOD, particularly, it was only related with our oxygen demand was only related with the this thing that I have highlighted, that is the carbonaceous organic compound that was estimated by BOD test. But now here, when we are going to see with the when we are dealing with the COD, now here COD means that we are going to find out the oxygen requirement for the oxidation of all the all the oxidizable matter. Now basically, let's understand one more difference between BOD and COD. BOD, if you see the definition, it is the oxygen required for the oxidation of the organic matter by the microorganisms, right? So it was a microbial test, right? Here, it was a complete microbial test. We didn't add any chemical oxidizing agent there. The oxidizing agent was itself, oxygen itself was an oxidizing agent in your BOD test, right? But here what is going to happen, I have to deal with the all type of oxidizable matter. So I can't rely on microorganisms. Microorganisms have very limited capacity of doing oxidation. So here I'll be dealing with something which is a chemical oxidizing agent. And here, a very strong oxidizing agent, that is K2Cr2O7, that is potassium dichromate, is it is going to be used. So in if you will be in normally oral in the orals, we ask students what is the oxidizing agent in BOD test. And now the student get confused. There is no such oxidizing agent in BOD test. The oxidizing agent is what it is. Oxygen itself is the oxidizing agent. And here, what is the oxidizing agent that we are going to add? It is the potassium dichromate. So even in the oral, so this particular type of question may be asked. Now here particular you can see BOD is the measure of the carbonaceous compound of biodegradable organic matter in a waste, whereas COD measures nearly all the oxidizable matter in the waste. Therefore, you only have given me the answer. COD for a waste is greater than the BOD value. This answer was given by you and it is the right answer, right? So both BOD and COD values of any waste are important parameters, as there is interrelationship between them, and that internship between them will be used for deciding which type of treatment is to be adopted for the waste, right? If COD is very much higher than BOD, then the waste is not biodegradable, right? If the COD is very high than your BOD, that means that what is meaning of if the COD is higher? If the COD is higher, that means that there are lot of inorganic oxidizable matter into that particular substrate, right? So no, normally in BOD we normally find out all this carbonaceous oxygen requirement. But if your COD value is very high than your BOD value, what it suggests that this particular factor, that is inorganic oxidizable matter, is very high. And because of that, what will happen? It won't be. So if it is naturally, if it is inorganic matter, so we can't treat it with the microorganisms. Hence, we can't give any biodegradable. Hence, we can't give any biological treatment, or the biological treatment is of no use here. Normally, such a waste, normally the waste having very high COD is from industries, because industries use lots of chemicals which are in chemicals, that means those are inorganic in nature, and because of that the COD value of an industrial waste can be very high. And normally if I have to treat any industrial wastewater, I do not go for biological treatment. I can't rely on microorganisms. Same has been given here. If the COD value is very high, the waste is not biodegradable. Biodegradability of a waste is indicated by the treatability index. Again, very important question with respect to your oral. So what is a treatability index? Treatability index is BOD upon COD minus BOD. So now what is BOD? Now let's break down this particular formula. What is BOD? Now here particularly it is the measurement of the oxygen for organic matter. And what is COD minus BOD? COD minus BOD is the measurement of the oxygen required for inorganic substances. So here organic upon inorganic, right? If organic is the organic is less, so in numerator you have organic and in the denominator you have inorganic, right? So if the denominator is on the higher side, what will happen is that this particular TI index will be less. If inorganic content is more, the TI value will be less, and if the TI value is less, you can't the waste is not biodegradable. You'll have to think of something different. So let's understand what kind of treatment are being given with the help of TI value, right? So now if my TI value is less than 0.5, less than 0.5 matlab kya hoga mera? If it is less than 0.5, that means that particularly the BOD or if it is less than 0.5, that means that TI value is less, and we already have seen if the TI value is less, the waste is it is not biodegradable. If it is not biodegradable, it is not amenable to biological treatment, especially the aerobic treatment. So what if it is not amenable to biological treatment? What will have to go? We'll have to deal with the chemical treatment. So the chemical treatment may be suggested, and the chemical treatment may be there can be various chemical treatment. For example, precipitation of the pollutants, coagulation, flocculation and the sedimentation, oxidation, adsorption, etc. So all these are the chemical treatments that we can give if the TI value is less than 0.5. Indication of TI value less than 0.5 suggests that the inorganic content is more, and to deal with the inorganic content, we will have to go for the chemical treatments. Now, what if my TI value is between 0.5 to 1? So if my TI value is between 0.5 to 1, it indicates that the biological treatment can be considered with the help of some nutrient supplementation. Again, if it is 0.5 to 1, that means that here also the inorganic content is more. But now in this particular range, we can opt for biological treatment, right? And now with the necessary nutrient supplementation. So for microorganisms to grow, we'll have to add some supplements in the form of nutrients, and then only we can go with the biological treatment. What if my TI value is more than 1? If my TI value is more than 1, that means that my organic content is more than this inorganic content. And what will happen if my organic content is more? My waste is amenable to biological treatment. That means that amenable matlab kya? What is the amenable? Amenable meaning is suitable, right? So it is suitable to biological treatment. Here, here also we got not amenable means it is not suitable to biological treatment. And here, if my organic content is more, naturally my TI value will be more than 1, and now the waste is now amenable to the biological treatment. So all biodegradable waste are chemically degradable. This is very natural. If I am having a biodegradable waste, I can even treat if I can even degrade it with the help of chemical. But vice versa is not true. If I am having a chemically biodegradable substrate, it is not always that it will be biodegradable, right? So however, for any waste providing biological treatment, it should be explored first, as it is more economical. So if I'm having any waste, what I will be doing is I will be exploring whether I can give biodegradable treatment or not, right? If I can't give any biological or biodegradable treatment, then I can go for chemical treatment. Why to go for biological treatment first? Because it is more economical, right? I do not have any cost of chemicals associated there. All my work will be done by the microorganisms which are available free in the nature. Also, when chemical treatment is adopted, whatever sludge gets formed need careful treatment before it can be discharged into the environment. Now, when we are going to do with some chemical treatment, maybe in the form of precipitation, coagulation, and all this oxidation adsorption, you will be getting some sludge, and also that particular sludge will have higher inorganic content. And again, it is very difficult to treat this inorganic sludge, and you need a very careful and very expensive treatment for that particular sludge. So always you have to find out explore whether you can give a biological treatment or not. So in normally examiner in the oral ask you if I am having I have a sample A and I have a sample B. He'll be asking you only this two. He'll be telling you only this two data, that I am having a bottle A and a bottle B, and I have to decide whether which treatment is to be given. He won't be telling you anything except this. He'll be telling one bottle A, one bottle B. There is certain sample. I don't know what sample it is. I've got that sample from some. I've got that particular sample from somewhere, and these bottles are now tell me which treatment is to be given. So now in that particular case, what should be your answer? So you should be telling the examiner that, sir, what I will be doing, I will be finding out the BOD value of that substrate or that sample. I will be finding out the COD value, and depending upon the treatability index, I will be deciding which treatment I will be giving. So whether to go for a biological treatment or whether to go for a chemical treatment. So he'll be asking you, so how on the basis of TI you will be deciding what is the answer? The answer is here. On the basis of this particular thing, I will be deciding whether to go for a biological treatment or a biological treatment with some nutrient supplementation or directly a chemical treatment, right? So now this particular type of understanding will be required, and that particular understanding will be tested in your oral because it is totally based on your understanding. Some PI values we have got for some of the waste that are also. So if I'm having a phenolic waste, so that means that it is a purely chemical waste. So the phenolic waste. So here you can see a phenolic waste has a treatability index of 3. So if it is a treatability index of 3, it is more than 1, and it is being treated with the help of the biological treatment can be done. So all this particular, so now even our domestic sewage, what we are learning here, the treatability index is 1.2, and 1.2 suggests that the biological treatment is good. Now you particularly see there are the metal plating industry. Metal plating industry, you see it is a 0.3. So when it is 0.3, what will have to go 0.3? It is no less than 0.5. So in metal plating industry, there is no option other than your chemical treatment. So all this, for even your soft drinks and all this synthetic textiles. So even we normally drink a lot of, or we consume lot of soft drink, but you will be very surprised to see that the treatability index is coming out to be 0.9. So imagine how high the chemical content will be there. So very high chemical treatment are, very high chemicals are there in your soft drinks, and hence it requires chemical treatment. So now you take decision whether to consume your soft drinks or not. Right? So paper and pulp industry also, though the paper and pulp is organic substance, but the treatability index is 0.7 because we require lot of chemicals. Basically, we require huge concentration of hydrogen sulfide, that is the sulfur that is used in the paper and pulp to get a white texture for that particular paper. So that, or even in the recycling of the paper, for example, newspaper. So if you are from newspaper, a different newspaper has been produced, but there is ink on the newspaper, and because of that, the entire pulp, paper pulp get a black color. To remove that black color, we need to add a huge quantity of hydrogen sulfide, and so because of that, the waste that is created has a treatability index of 0.7. So this is for your information, and to particularly get, you can judge whether how high or how low the chemicals will be there into this. Now let's understand what is the importance of COD test. Now as of now we have understood what is COD value. Now let's understand if the COD test is really important to be done, or now what are the values that we are going to get. Now these values can be applied. Now COD value indicates practically the overall pollution strength of a raw waste, domestic or industrial. So it is very useful that you will be getting the overall pollution strength, right? And the COD value is universally globally accepted for the designs of your all the treatment units, right? So it is very, very important to find out the COD value. COD and BOD values of a waste are used for determining the treatability index. So treatability index, depending upon the treatability index, the designer gets an idea whether to go for a biological treatment or a chemical treatment or something like that. Now this COD test, COD test you can perform, complete COD test can be performed within 5 hours. So COD test is a quick evaluating performance. It evaluates the performance efficiency of a treatment plant in a very quick manner, right? It requires only 4 to 5 hours, and corrections can be immediately adopted, or if there is any error, you can immediately adopt any correction for your STP, right? As the test can be done in 3 hours, but not 3 hours specifically. 3 hours is a very optimized time. You require at least 4 to 5 hours for this. And if you compare the BOD, so BOD requires at least 3 to 5 days. Now you can judge whether to know how important that COD test is there. So if I have to take quick decision, if I have found some fault in my STP, and I have to check whether my performance of my treatment plant is going on in a very good manner or not. So I won't be doing a BOD test. BOD test will be requiring 3 days or 5 days, right? Depending upon the temperature. But COD can be done in 4 to 5 hours, and hence it quickly evaluates the performance of your treatment unit. And if there is any error, you can apply the corrections immediately, right? So you don't have to wait for a day. Even in the in 1/4 of the day duration, you can complete the COD test and start with the application of the corrections. By knowing the general COD by BOD ratio, BOD value can be worked out in an emergency form of COD test result, right? So if I know what is the COD by BOD ratio, so this is the normal COD by BOD ratios published by many of the researchers in their literature papers after doing some experimentation. And though if I know what is the COD by BOD ratio, I can find out if BOD value of my COD is known, and I can find out COD value of my BOD is known. So that is very important. Now COD test is used for determining the suitability of the treated waste for disposal, right? So even if my STP, even if my STP is treating the wastewater, so whether the end, no, whether the treated water coming out of the S2P can be used in some different format or not, that can be decided with the help of the COD test value, right? Of the COD test. Now, no, particularly it is okay that the COD test should be done and has a higher significance than the BOD test. But let's see what are the limitations. The test adopts an artificial procedure. It cannot differentiate between the biologically degradable and biologically resistant organic matter, whereas BOD test simulates condition obtainable in the natural stream. So what is in BOD test? We rely upon microorganisms which are present in your natural stream as well, and hence it is a purely natural process. But what is this COD? It is purely an artificial procedure. We are going to perform the oxidation, but it is a chemical oxidation and it is an accelerated chemical oxidation procedure. Mark my word, what is a COD test? What is the difference? One more difference I'm telling between the BOD and COD, right? A BOD test is it is a natural oxidation, oxidation happening with the help of the microorganism. And what is a COD? COD is an artificial oxidation happening with the help of a chemical oxidizing agent at a very high temperature. So when I say at a very high temperature, that means that it is 150 degrees Celsius. And why we have kept the temperature as high, that is 150 degrees Celsius? Because we want the results in less time. So what we have done is, by increasing the temperature, we have accelerated the chemical oxidation process. So chemical oxidation in itself is fast, but we have accelerated it more. How we have accelerated it more? By increasing the temperature. That is, we have set the temperature to 150 degrees Celsius. So when I say that 150 degrees Celsius, so it is the temperature, design temperature of this test. So tomorrow, if you wish to complete this test in, say, 1 hour only, so you can't increase that temperature to 250 degrees Celsius. So this is the design temperature for this particular test. So it is 150 degrees Celsius only. You can play with the temperature. It is 150 degrees Celsius for a chemical oxidizing agent potassium dichromate, in which you obtain a result in 4 to 5 hours, right? COD test does not indicate time-wise the rate and the extent of the removal of the pollution load of a waste in a nature. So now, whereas BOD1, BOD2, BOD3, BOD20 indicate the natural rate of biodegradation of a particular waste. So now, particularly, I can normally we find out BOD5 at 20 degrees Celsius or BOD3 at 27 degrees Celsius. But I can even find out what is the BOD after 1 day. I can find out what is the BOD after 2 days, BOD after 3 days. So what I will be getting a stage-wise or time-wise values of BOD. But that we cannot do in COD, right? COD we are directly going to get the final value of the oxygen that is required. So these are some of the restrictions that we have got, or the limitations that we have got with the COD test. Now, what are the standards recommended? So industrial effluent discharge into the inland surface water. So if I'm having any industrial effluent, I'm treating that industrial effluent, and now that I want it to be discharged into the inland surface water. So what is the COD? What should be the COD? It should be 250 mg per liter. Similarly, if I am having any industrial effluent and that I have to discharge into the marine coastal area, so that particular value is again 250 mg per liter. So when it is even for the sewage, the values are 250 mg per liter only. So the discharge standard, the maximum allowable limit for the sample to get discharged into the inland surface water, for example, river or a lake, or in marine coastal area, for example, sea or ocean, is 250 mg per liter. If it is more than that, we'll have to treat that sample, reduce its COD to 250 mg per liter, and then only we can discharge. Now, when we are going to consider our sewage, the sewage has a normal COD of normal COD in the range of 400 to 500 mg per liter, and with the help of all this STP treatment that you are going to do, so all this your sewage treatment plant is going to reduce the COD of sewage, which was like 500 mg per liter, to half, that is 250 mg per liter, and then it is particularly said that it is safe to discharge that sewage into the inland surface water or a marine coastal area, right? So no, even 250 mg per liter is more, but what happens is that when we discharge the treated sewage into the water, or even in this case the industrial effluent into inland surface water, we assume that the natural cleansing process will happen, and further with the help of the microorganisms that are present in the soil, the COD will be reduced from 250 mg per liter to lesser value. So that we are assuming, right? So that the natural cleansing process will take place. But nowadays our river itself the river itself is a blackish, it is having a blackish water, and then too we are adding some effluent sewage into it. So it do not have there will be no natural cleansing process that will be happening, and the COD value will remain unaffected, and it will be very high. Now we are going to discuss the principle of COD, and then we are going to stop. So half part of this is already being discussed. I will be just reading. A known value of potent oxidizing agent is used to oxidize all the oxidizable matter in the waste sample as completely as possible. Oxidation is carried out at an extended period at 150 degrees Celsius. The residual oxidizing agent is estimated using a suitable reducing agent. The amount of oxidizing agent consumed is a measure of the overall pollution load of the waste. Now this is somewhat you will be seeing that many times this principle of experimentation is somewhat confusing, or it is difficult to understand. I'll be trying to break it for you, and if you understand this principle, all the COD experimentation is now all the COD experimentation is understood, right? Now what is happening? They are saying that a known volume of potent oxidizing agent is used to oxidize all the oxidizable matter. So what is a potent oxidizing agent here? The potent oxidizing agent is the K2Cr2O7 with 0.25 normality. So we are going to use 0.25 normal K2Cr2O7, which is going to oxidize all the matter. Now they are saying that a known volume. What is the known volume here? The known volume that we are going to add is 10 ml, right? So here 10 ml of K2Cr2O7 will be added into the waste, and it will be used for the oxidation of all the oxidizable matter present in that particular sample. The oxidation the oxidation reaction will happen for an extended period. Normally it is 1.5 hours at 150 degrees Celsius. So I think up till this particular part you have understood. I am repeating. The meaning of this particular sentence is that 10 ml of K2.25 normal K2Cr2O7 is added to completely oxidize all the oxidizable matter at 1.5 hour at 150 degree Celsius. The residual oxidizing agent is estimated using a suitable reducing agent. Now this particular sentence is very, very important, and this, if you understand this, next two sentence you understand the COD experimentation, right? So what they are saying is that the residual oxidizing agent is estimated. So here we have added 10 ml. Now we are going to measure out of this 10 ml how much oxidizing agent, that is how much K2Cr2O7 is used, and the remaining oxidizing agent is called as the residual oxidizing agent. So the 10 ml that I have added, the 10 ml K2Cr2O7 is I have added. How much K2Cr2O7 is being utilized from that 10 ml, right? So now how that I'll be finding out? That I'll be finding out with the help of a suitable reducing agent. And a suitable reducing agent here is ferrous ammonium sulfate, right? So that will be ferrous ammonium sulfate is going to act as a titrant, right? So here I am going to find out how much K2Cr2O7 is utilized with the help of a suitable reducing agent, right? Now the amount of the oxidizing agent consumed is measure of the overall pollution load of the waste. So the volume of K2Cr2O7 that I require is nothing but the pollution load of that particular sample. How much K2Cr2O7? Why we have added a K2Cr2O7? To oxidize all the oxidizable matter. Now if all the oxidizable, let's say I have added 10 ml, and out of 10 ml only 5 ml is required for oxidation of all oxidizable matter. That means that I have utilized only 5 ml, right? If there is another sample, it requires 9 ml to oxidize all the oxidizable matter. So what is the difference between these two samples? The second sample, which requires 9 ml to oxidize all the oxidizable matter, that means that it has higher quantity of oxidizable matter. That means that it requires higher oxygen. It has the higher oxygen demand. That means that it has higher COD. The first sample, which required 5 ml of K2Cr2O7, that required for total oxidation of oxidizable matter, that we can say that it comparatively has less oxidizable matter, hence it uses less potassium dichromate, and hence it requires less oxygen for the it requires less oxygen, and hence has less COD. So it is as simple as that. So I'll be just repeating this entire, I've broken down this principle for you. I'm breaking it down again. So I'll be using 10 ml of K2Cr2O7, and I'll be adding it to oxidize all the oxidizable matter. I'll be carrying out that particular test at 150 degrees Celsius for 1.5 hours. After that, I'll be finding out how much of the potassium dichromate is required for the oxidation of all the oxidizable matter by using ferrous ammonium sulfate, and the amount of potassium dichromate that is required for the oxidation can be related to the overall pollution load of the West. Now, I think that I've made you understand this principle in the easiest way possible. So now there are some discussions. Oxidizing agent. So here we have already said that we are going to use K2Cr2O7. It is readily available in the pure analytical form, and the standards prepare retain their normality for a long period. Right? Acidified dichromate oxidizes nearly all types of organic matters into CO2 and water. Right? So here acidified dichromate is required. So particularly there is one more chemical that will be required. Here I told you that we require K2, here potent oxidizing agent. I've told you the name, that is K2Cr2O7. Here I have told you suitable reducing agent, that is ferrous ammonium sulfate. Now they are saying that they acidified. So for need of acidification, we are going to add how much? We are going to add 30 ml of H2SO4. Right? So here 30 ml of H2SO4 will be added here for particularly for providing the acidified condition. So the reaction that will be taking place is this particular reaction. So the reaction is is being given here. Now the color of the dichromate is orange, and it helps in recognizing the presence of the residual dichromate after heating, which is essential for the success of the test. Dichromate consumed during the test is the difference between the dichromate concentration at the start and the dichromate concentration remaining as excess after the hot digestion. The initial concentration of the dichromate is estimated by running a blank through the test, which will practically eliminate error due to any oxidizable matter. So this we will be seeing when we are going to perform the practical. As of now, there is no need of understanding it. Reducing agent, I've already told you, this is ferrous ammonium sulfate. The ferrous ion reduces the dichromate completely as excess of Fe2+, giving a sharp reddish brown endpoint with a ferroin indicator. You also have this particular into consideration, this test. Now the COD formula that we are going to use is A minus B into normality of the titrant, right, into equivalent weight of the oxygen, because we are determining the oxygen requirement only, into 1000 into DF, that is the dilution factor, and the volume of the sample in ml. So what is A? A is the ml of the titrant used for a blank. So particularly what is a blank? We are going to find out the potassium dichromate utilization for distilled water. So potassium dichromate utilization for distilled water is represented by A, and B is nothing but the potassium dichromate utilization for your B. So A will be on the higher side because it is distilled water, you do not have any pollutant, and B will be on the lower side because it has the pollutant, and there will be more potassium dichromate utilization here. So A minus B will be always positive, and you will be getting the value of COD in a very simplified manner.
So we are going to perform the standardization process for ferrous ammonium sulfate, which is the titrant for our COD experimentation. The solution that is prepared for FAS is of 0.1 normal. So the 0.1 normal is required for the titration purpose. Here, after preparation, we are going to check whether we have prepared 0.1 only, 0.1 normal FAS, or there is some change in because of our preparation or because of some climatic effect. So this is how the FAS solution looks like. It is a bit transparent, but it has a luster, because luster, and because of that, it has got a sparkling effect. So this is the ferrous ammonium sulfate that we have. Right, so we are going to find out its normality. So the very first procedure according to the manual is to take 10 ml of 0.25 normal K2Cr4O7. So that is 0.25 normal potassium dichromate. I've measured, actually it is 10 ml, so you can measure it via pipette or even your measuring cylinder. So 10 ml of potassium dichromate has been taken, and it is 0.25 normal. After that, we are going to add 100 ml of distilled water to it, right? So 100 ml of distilled water is to be added. So it is to be measured via measuring cylinder. And we are going to add 100 ml of distilled water. Right? After that, we are going to add 3 ml of concentrated H2SO4. So now, this is the concentrated H2SO4. We are going to require it in high quantity for the COD process, because the quantity that we have to add is 30 ml. Previously in DO experimentation or BOD experimentation, we have used this only 2 ml, and that we had measured with the small 10 ml measuring cylinder. But now the quantity is very high, that is 30 ml, and you will have to be very careful by adding while adding this concentrated H2SO4 into this conical flask. Now this conical flask consists of a part of liquid, part of water, and when we will be adding concentrated H2SO4 to it, what will happen? There will be some reaction, right? A bumping reaction may take place, and that because of that we have to add it very, very carefully. So I'll be telling you how we are going to add this. So we have already measured 30 ml of H2SO4. So while adding it, you have to make it slightly. You have to hold it in this position, and you have to add H2SO4 slowly, right? Slowly and continuously. I guess you can hear a voice that is coming when this H2SO4 is reacting with a liquid below. The face of the conical flask should be away from your face, right? There are chances that the fumes will come out. You shouldn't have any contact with your fumes, so the fumes shouldn't enter your nose. And there is a heat, it is the exothermic reaction, and the conical flask is going to get heated, right? So if you check, if you see, the temperature is very, very high here. Right now, this is an exothermic reaction. The temperature is high, so we are going to cool this liquid for a few minutes. So we are going to keep it for cooling purpose. Now this reaction, this cooling is very, very important. If you don't do cooling properly, what will happen is that the amount of ferrous ammonium sulfate that will be required will be very less, and because of that the normality that will be calculated and will be used further in the calculations will be also very less. So even though you are preparing a good quality exact normality FS, so because of this liquid being hot, there are chances that you will be getting the wrong normality. Right, so we'll be waiting for like 5 to 10 minutes. We'll be waiting, and after that we are going to start with the titration. So when we are going to start with the titration, we are going to add the ferroin indicator here. So the ferroin indicator, when we add this ferroin indicator, we'll be getting a slightly, you'll be getting a dark green color, and the end point of this titration is a stable brown color PPT, right? So we are going to achieve that particular color. So we are going to wait till it gets cool. We have cooled this sample. Now the next process is to add the ferron indicator and start with the titration process, right? So for 3 to 4 drops are sufficient, right? So we have added this ferron indicator, and now let's start with the titration. The titrant we have already filled, which is ferrous ammonium sulfate of 0.1 normal. The drop by drop addition and simultaneous stirring will be required. The end point of this is a stable brown color, right? There are various color changes that are happening. You can note down the changes as well which are happening. So now this is a yellowish liquid that we have. So when we do titration, the color is going to change. Slightly different color than the previous color has now occurred. Again a different color. A different color. Now this color will disappear and the red color will start to appear. Right? So this is not a final color that we have obtained. After this color, we are going to get the final color. You can see the color changes happen. You should go very precisely drop by drop. The color has escaped, but this is not a final color. You can see that the red color, it was a brownish red color that has obtained, and it is also stable. One more drop for the correction. And the reading that we have obtained, so this is the final color that we have obtained, and the reading that we have got is 24.8. So this reading will be further used for the calculation of the normality. The formula remains same. N1V1 is equal to N2V2. And here N1 is nothing but the N1 is the normality of potassium dichromate, which is 0.25 normal. V1 is the volume of potassium dichromate, which is 10, right? And N2V2. So N2 is the normality that we have to find out of the titrant, which is unknown, and V2 is here now 24.8, right? So if we just do some calculation, so here the calculation part, so it is 0.25 into 10, right, divided by 24.8 comes out to be 0.100. So it is an exact normality that we have achieved of 0.1 normal, right? So 0.1 normal we have achieved, and this particular normality will be used for further calculations of the COD value. So we are going to start with the experimentation procedure of COD experimentation. The very first step is that we need to take 400 milligram of the mercuric sulfate, that is HgSO4. So we have this mercuric sulfate with us. 0.4 milligram means 0.4 gram. So we are going to measure it on the scale, right? So 0.4 gram of mercuric sulfate. Approximately 0.3 now. So we have measured 0.4 gram, and we are going to add it directly to the COD flask. Right, so we have taken 3 COD flasks. Now 2 will be used for the same dilution, and this is for the blank purpose, right? So I am adding it in the blank as of now, and then I will be adding it in the, you can see the yellowish color that you have got, right? Okay, so we are expecting the COD value for this sample to range, in like 400 to 500. So we don't know exact value, but it may differ in the range of like 300 to 500. So correspondingly, the dilution factor that we can have to take according to the dilution chart is 1. So here we are going to directly take 20 as a sample. If it would have been some different dilution, then double dilution, triple dilution, same as we have seen in the case of BOD would have been adopted. But in this particular case, we are only going to keep one single dilution. What we are going to do is that we are going to keep 2 flasks for the same dilution. Why so? Because it requires 1.5 hours, and there is a lot of energy that is being imparted for this reaction. So at a time we can keep like 15 flasks for the dilution purpose. But if we, to avoid some last minute failures, so what we will be doing for each dilution, it is recommended that you need to keep 2 flasks. In our case, we are going to keep only one single dilution. So for one single dilution, we are going to keep this 2 flasks, and blank flask will be acting as a reference. So the next step is to add 20 ml of sample into each of this flask. Now remember, your distilled water. Right? So the distilled water for the blank, your distilled water in itself is a sample. So in blank we are going to add 20 ml of distilled water, and in all other these 2 flasks we are going to add the 20 ml of the sample. So sample in our case is this particular lake water that we have collected. So that we are going to add. So as of now I am adding it into the blank. So I am going to measure 20 ml distilled water. I am going to add it in the blank flask. Right? Just a minute. I'll be washing this properly. To avoid some failures, because this is our very reference flask. So we have added only HgSO4 in all this, all of this digestion flask, COD digestion flask, right? Next is 20 ml of sample. So we are going to stir it properly. The sample, in many cases, the smaller particles which are having some high specific gravity may get settled. So what we are going to do is we are going to stir it properly, and then we are going to add 20 ml in each flask so that the effect remains proper. Just 20 ml. I'm going to add it in the flask. Dilution that is adopted is 1, right? We haven't written any tag. So if there are different dilutions, you can tag this COD flask, put a sticker onto it regarding the dilutions and the flask number. We added the sample in each of this keys. The next procedure is now to add, according to this procedure, we have to add 10 ml of 0.25 normal K2CR407, which is our reducing agent, right? A very important liquid. So 20 ml of sample is being added. Now we are going to add, with the help of pipette, 10 ml of K2CR407, which has 0.25 normality in each of this flask. This was the blank. Right, so we have added 0.25 normal K2CR207, which is going to act as a reducing agent in our case. Right, now according to the manual, the next procedure is to add 30 ml of concentrated H2SO4 in each of these flasks. Right, so very carefully we are going to complete this procedure. I will be moving to this wash vessel. And I will be adding the H2SO4 in all the. So previously also at the time of the titration we have added it into the conical flask. Here we have to put it in the dilation flask. The utmost care is to be taken. Right, there is no stepwise addition, or you can say a slow addition of H2SO4 is to be done. Otherwise, the sample may get failed because the shock loading of the acid is not recommended here. So same thing, you have to hold your digestion flask away from your face. The face of your digestion flask should be away, so that even if there is a bumping action, if the acid is thrown outside, it won't harm your face. And again, the fumes are not going to enter your nose, right? So, proper care, and you will be having a less risk. A very slow addition of acid is recommended. No stirring, nothing is to be done, right? If you do stirring, the reaction will take a violent turn, and the liquid will come outside, right? So you can see the change that has happened, right? So this is regarding your blank sample, right? Next, we are going to repeat it for the both of the flasks both of the flasks with the same dilution. Here you can see we have added acid of the 30 ml acid into all of these flasks, right? The next procedure is to add 200 milligram of silver sulfate, right? So 200 milligram properly we are going to measure it. I'll be showing it how we are going to add it. It is just in the powder format. 200 milligram means 0.2 gram. A very small quantity. It's okay if it is a bit higher, because the quantity is also less. Okay, yeah. So we are going to add so much amount into each flask. So I am going to add it in the Alright. So same way we are going to add it in the other two flasks as well. So we have added all the chemicals here. So the next thing is that they have told us to add 2 to 3 glass beads. So why addition of glass beads is there? Because we are going to heat these sample at 150 degrees Celsius for 1.5 hours. So what may happen is that during this reaction, the liquid will boil, and it will try to come out of this particular flask. So addition of the glass beads will they will be suppressing that heat reaction, or they will be absorbing the heat. So I'll be adding glass beads into it. It are just the glass particles that we need to add. So 2 into each of this. So that the pumping action will get avoided. So the next procedure according to the manual is we'll have to attach the reflex condensers into it. We are going to add, we are going to particularly attach the reflex condenser. So I'll be directly taking it due towards the COD digester that we have in our lab. Right, so this is the COD digester what we have. We are going to keep the sample that we have with us in these. There is ample space, so we'll be keeping it alternately. Okay, we are going to attach the reflex condensers. So 3 reflex condensers will be required. So this is called as a reflex condenser. I will be telling you what is the use of the reflex condenser. So when the sample is kept at 150 degrees Celsius for the digestion purpose, the fumes will get the fumes are going to come out. So we need to catch those fumes as well. So all those fumes will get collected here, right? And after some time they will be again falling into this particular condenser, right? So COD digestion class. So this is called as the reflex condenser, right? So I'm going to attach So we have attached this. We are going to start the COD digestion flask. So we have started our COD digestion, right? So here the entire accelerated thermal digestion or oxidation process is going to happen. So here we have set the temperature to 150 degrees Celsius. This is the current temperature. So we have to heat this, keep this for 1.5 hours at 150 degrees Celsius. After this 28 degrees Celsius is reached to 150 degrees Celsius. So after that 1.5 hours of particular heating is to be done. So approximately you will be requiring 2 hours of heating. So 1.5 hours for 150 degrees Celsius and that 0.5 hour, initial 0.5 hour to reach the 150 degrees Celsius, right? So we have to keep this for COD digestion for 1.5 hours, and then we'll be doing some steps are to be done, and then we are going for the titration process, right? So we have completed 2 hours of digestion, right? So we are going to switch off this digestion process. Now what is the next step that we have to do is we have to settle this all fumes inside this COD digestion flask. So what we are going to do is we are going to add 20 ml of distilled water into each of this 20 ml of distilled water into each of this COD digestion flask through reflex condenser. So what will happen, all those will get settled. So here I'm adding it slowly. ml distilled water. So I've added 20 ml distilled water, so I'll be removing the reflex condenser to avoid the confusion, and I will be putting it in this tank. Directly into the same process is to be repeated for other two, 20 ml each. Removal of reflex condenser. Last 20 ml. A bit slow addition is required. After that, a very important step, what we are going to do is we are going to remove these COD digestion flask, and then 70 ml of distilled water in each of these flasks to be added, right? So firstly 20 and now 70, so that means total of 90 ml of distilled water is being added. You will be seeing a completely filled COD digestion flask after addition of 70 ml of distilled water. right? So now the next step is to cool this digestion flask properly, make it to the room temperature, and then we are going to do the digestion, right? So each of this digestion, we are going to empty each of this digestion flask into the conical flask, so that a better surface area is available for the cooling purpose, right? So very properly you will be removing all the substrate. You have to remember, because conical flasks do not have level, right? So you will have to remember which is which sample, right? So this is the blank sample that we are taking out. To be done a bit slow. You can even take the glass flask, right? So similarly, we are going to empty all this into the conical flask. We are going to cool it. We are going to add a ferrine indicator, and then we are going to do the titration process, right? So we have emptied the sample in the flask. The next step is just to add the ferrine indicator and do the titration process. Just a second. बंद कर दे, वीडियो कॉल We have emptied the COD digestion flask in the conical flask. The next step is just to add the ferrine indicator and to do the titration against FAS, and the endpoint color is the stable brown color. Yeah. So yes, we have added the 4 drops of ferrine indicator. Now let's start with the titration process. As you can see, there is no green color that is obtained, right? So if it would have been like green color development, so it would have been the failure. But here no green color development immediately after COD digestion has occurred. So let's start with the titration part and observe the color change. The color that we require is stable brown color. The value of this ml of titrant will be noted as A, because this is of blank. Observe the color change that is happening. right? So we have obtained this, no, reading is coming out to be 24.9, right? So here you can see the color change has happened, and the A reading has come out to be 24.9, right? For blank, right? So the blank reading was 24.9. We are going to no, do the titration for sample. We are going to add, Ferron indicator, and let's start with the titration process. Right? Again, drop by drop addition. So the color obtained is now it is brown stable color, and the reading that we have obtained is 14.2, right? So now we are going to do the similar titration for our next sample as well. We're going to add Ferron indicator. And let's do the titration. Right, so drop by drop addition is required for doing the titration process. Right, so observe the color change now, right? So yes, a stable brown color is obtained, and the reading that we have got is 14.6 for this sample, right? So nextly we are going to do the calculation and find out the COD value for this sample.
We are going to see the calculation part of the COD. The very first thing is we have to find out the normality of the titrant. So we have done the standardization process. During the standardization, we have got the volume of titrant as 24.8 ml. Substituting it into the formula of formula N1V1 is equal to N2V2, will be getting the normality as zero point 0.1 normal for FAS, that is ferrous ammonium sulfate. For COD determination, we have the formula A minus B into N into 8 into dilution factor divided by 20 is equal to the COD in mg per liter. If the dilution factor is going to change, we'll have to vary this value. For the experimentation that we have done, the dilution value was taken as to be 1, dilution factor is 1. For A, which is in the formula here, which means the volume of the sample required for, or volume of the titrant required for the blank, it is nothing but 24.9 ml. The value of B, which is the volume of the titrant required for the sample, is 14.2 for the flask B and 14.6 for the flask C. Putting these values into the formula, we'll be getting the further values. So substituting the values, 24.9 into normality, that is zero point 0.1 into 8 into 1000 divided by 20 is equal to 428 for the flask B. Similarly, for the flask C, substituting the value 14.6, we get a value of 405. As these are for the same sample and the same dilution, we can take out the average, and we get the average value of COD for the sample under consideration as 420 mg per liter. Now the value is greater than 250 mg per liter, which happens to be standard of disposal for sewage water, and it has been written in remark that 420 mg per liter is greater than 250 mg per liter. In the conclusion, the COD value of the lake sample is 420 mg per liter, which is greater than 250 mg per liter, which is the standard for the disposal. Hence, the lake sample needs the suitable treatment to reduce its COD value to 250 mg per liter before its disposal.